Good. Yep. Okay, like I said, it's the first class. We are going to learn some transformation. Oh gosh, I only have 5 minutes left, right? Oh no, yeah, 1:45. Sorry. Okay, I still get used to the teaching mode. Good. So it's from Kazan-Berger. Hold on. It's from Kazan-Berger 2.1 and then 4.3. What is transformation then? So in this introduction, you could actually ask yourself, okay? So if I have notation right here, x follow normal 0, 1. Okay, hold on. I want to change my, could I? Yeah, it's too thin. It's too thick. Okay, so if x follow normal 0, 1, ask yourself, what the distribution, what is the distribution of x squared? Okay, if you don't know it right now, it's okay. But if you don't know it right now, you possibly need to pay an extra effort in this class. After this one, you are going to know that it's chi-squared. You are going to know that it's x normal 0, 1, x squared is going to follow chi-squared 1, equal freedom. Okay? Then I will teach you how to derive it. But you may know that, already. Okay? In other case, if x is uniform 0, 1, then what is the distribution of minus log x? Okay, then after this class, you're going to know this guy's exponential 1. Okay, good. So what is a transformation means then? It's really nothing but you got original PDF, right? Then I do some function on that original PDF. For example, x squared is apply a function x squared, a square function on it, x, to become x squared. Then the same thing is minus log x is also a function to apply original variable x. Okay, hopefully these two distribution become your nature after hopefully these two distribution become your nature after this class, which means whenever you see x normal 0, 1, you would know automatically x squared is chi-square 1 already. Okay, good. This kind of function transformation is so obvious to you, I think. But one of things less obvious is if I f x is exponential lambda, and then what is the minimum of x1 to xn? Okay, we call it minimum order statistics. Okay, so that one to us also transformation because these guys are my original variable. Minimum is some function I can apply to original variable x1 to xn. So this guy also transformation to us. Then as long as there's a transformation, as long as the original distribution right here, then you need to derive in what this guy follows. Okay, not as straightforward as these two guys right here. But after this class, you should know how to derive in the distribution of minimum order statistics. Okay, good. The first three cases are the so-called univariate, okay, which means only single variable. Okay, and then in the transformation we are going to learn about multiple variable as well, also called multivariate. Okay. Okay, the first one is if x follow exponential lambda, y follow exponential mu, then if I assuming x square independent, then how do I know x minus y follows? Okay, or further, it's not only about difference between x and y, but also x divided by y, as a ratio between x and y. Okay, so if we are good enough, you possibly know that it's what does x minus y will follow then, right? I give you 1 second to think about it. Usually in person, I'll consider you guys, and I will know. I'll give you like a time to try to say something about what this guy will follow, right? Okay, so hopefully after this class, this guy also become intuitive to you. X exponential, y exponential, x minus y is going to be exponential. Okay, if lambda bigger than mu, it becomes exponential lambda minus mu. Okay, these guys are these kind of things are intuitive. I've been teaching this guy for 8 years already, so this something is really intuitive to me. But you could derive it mathematically, and in the meantime, it's x and y follows what? Okay, x and y, x exponential, y exponential. Exponential is a gamma distribution or chi-square distribution. You know, this guy gamma, this guy gamma, this guy going to follow F distribution. Okay, but again, as I know that, but not necessarily you guys know that right away. But hopefully after this class, you know that. Okay, intuitive. So then, if you learn about 660, you will know. If I talk about this guy right here, this guy is marginal, right? This question right here, find the distribution of x minus 1. To us, it's called marginal, okay? But in the meantime, it's because they are multivariate. Even doing transformation, still multivariate. If that's the case, you could talking about something called what? Join PDF, right? So that means I'm not only talking about marginal of some univariate random variables. Because it's two variable system, I can, after transformation, I can also talk about something jointly, or the joint PDF. Okay, so that means in this things, this kind of fundamental surviving skills. Going for moving on. Okay, good. Good thing is that's what Kassenberger, the book is so good. That's because you could find a page 627 in Kassenberger. You will see those like a dot box and the arrows and then bunch of things connected to each other about the relationship between distributions. Okay, this document I'm going to upload to Sakai. Okay, I have that PDF file scan. I can upload it. The reason I say so is this kind of distribution table is some document I'll give it to you. You'll be given in a master exam as well as additional table to your cheat sheet, which means if you're working on cheat sheet before, you don't have to working on saying like, you know, like what's the form of the exponential PDF. You don't have to do that. Okay, I'll give you this kind of distribution table. You could see that already. Okay, so I will put a copy on that. You could download it from Sakai. Okay, what such questions, right? So we are statistician or biostatistician. We make a living for summarizing the data. Right? Data coming out, you are trying to make a statistical inference using the data. Okay, so this kind of things like sample mean and sample variance is something you using as a quantity frequently in our real life. You communicate with people about percentage, right? And then average salaries of professors, something like that, right? And then so then you do need to know the distribution of the statistic you are using. Okay, if you say I'm going to using sample mean to communicate with you, then you need to know about the distribution of sample mean. So you would do the statistical inference, for example, do hypothesis testing or construct a 95% confidence interval around the sample mean, for example. but you do need to know distribution of a sample mean. Okay, so so-called under given model, I particularly point out right here is model in statistics confusing to me. Okay, model to you guys, you imagine regression, right? Logistic regression model. Okay, so model in a lot of textbook, especially if like statistician write it, model basically is PDF. Okay, so if you look at, for example, look at Hogan Craig book, they will talk about some model. Okay, the model is not the model imagined like logistic regression or linear regression. It's a model. PDF itself is a model already. Okay, so then in order to use the summary statistics, okay, so like I said, it's mathematically we just form a statistic as a transformation from data. That's it. Okay, good. Great. Then let's go to some mathematical stuff. Okay, 36 right now. I have 9 minutes. Okay, so in this class, we are going to learn, I can talk, right? You and I can talk, you and I can communicate. But in terms of writing, in this class, it's important. It's how do I write something professionally? Okay, I can say, well, if I said right here, right, well, I said statistic transformation of data. Then how do you write that in mathematical formation? That's something you want to learn in this class. Okay, good. So if I want to write something mathematically, is this. Say X is a random variable, right? Random variable right here. Who's PDF or PMF, right? PDF for continuous variable, PMF specifically for a discrete variable. And then if we want to find the distribution of y equals to gx, right? G is a function right here. Okay, so if you're confused by say G is a given function right here, then you need to talk to me. Okay, so I need to know your background is. Otherwise, sometimes I'm talking something like I said is you have to understand. So if you feel like well, a G is a given function, what does that mean, right? So then you have trouble. So then you need to talk to me. Okay, so then we will define this kind of script S right here. Okay, becomes so-called sample space. Sample space means like I have like a collection of data right here. Okay, collection of sample becomes sample space. And then if this is sample space right here, basically is including those X right here, which have PDF bigger than 0. That basically is a mathematical expression. Okay, nothing but talking about where we define these sample spaces. And then after doing transformation, Y become a new sample. They of course they have a new sample space right here. And then I'll write is their element Y right here. This is my transformation for every X right here in the X sample space. I do G function transformation to a new sample space that's a Y. Okay, so this kind of set right here, such X and Y, okay, because support set. That means that this guy right here, if X bigger than 0, is a support set, indicating whether or not your X only coming from the positive domain. For example, exponential, right? In 660, you write your PDF down. Normally, I think Anastasia is going to say, hey, do I come on? Then write a domain of an X sample. It's, for example, if you write PDF exponential, you'll write common X bigger than 0. Okay, to indicate that's the logic domain of X. X can only happen when they are positive. Okay, if I write in a PDF of normal, right? Maybe I can write it right here. Why I keep talking, right? So if I write in down F, it's normal 1 square root 2 pi sigma square exponential minus 2 sigma square, then X minus mu square, then right here, right? If I write it, people will say, hey, how about X domain? Infinity to infinity. This is the domain support. Okay. In the meantime, possibly instructors told you that also is how about mu and how about sigma square. Okay, that's become permeable space domain. For example, this guy also coming from minus infinity to infinity right here. But sigma squared is what? You got to be bigger than 0. Your variance won't be negative, not even zeros, for example. Okay, so that means in this class or in like your masters, if you learn about PDF, then pay attention to what domain of PDF is. Okay, good. So then, what is the transformation of discrete random variable, which is actually very easy to derive? Okay, so it's no more like a simple counting. Okay, for example, if x is Poisson, lambda, I pronounce Poisson. Okay, if you like prefer pronounce Poisson, well, it's okay. We all mutually understand what that means. Okay, but when I say Poisson, understand what I'm saying. Okay. Yeah, well, you do know Poisson is French, right? Somebody say Poisson is more close to French, but I do know French. I don't know if that's French. Okay, whatever. So if I say x Poisson lambda, then if I say, remember I say this transformation, you see that, right? You see it in the introduction slides. If x is exponential, then what is x squared? If x is normally 1, what is y equals to x squared, right? Then the same thing right here. If x is Poisson, then what is the distribution of y equaling x squared? X is discrete. You got to know that, right? You got to know that. Then if x is discrete, then the distribution of y nothing but counting. Okay, for example, it's how do I calculate the probability of y equals to 25? Right? It's really if x is 25, nothing but x equals to 5. Right? Then you ask yourself, you are saying is y equals to x squared. Where is the probability of x equals to minus 5 then? If x5, x minus 5, x squared also 25, where does this guy go? This guy is not necessary because x by domain of Poisson, x is going to be from 0 to 1 to 2 to to infinity. Okay, Poisson counts neighbor negative. So this guy is basically 0. You don't even bother to write it. Okay, that's how important you know the domain is of the some random variable. Okay, then things but nothing but counting. So probability of x equal to 5 by Poisson's PDF, right? You could pull out the PDF, the distribution sheet, right? You know that, right? If it's lambda, so factor x factorial, then lambda x e minus lambda is a PDF of Poisson lambda. Okay, so right now lambda. Okay, good, right? So then of course you say x is from 0 to 1 to Then the probability of x equal to 1 is what? Nothing but plug in of 5 into where x should be. Okay, that's it. You finish. You're actually deriving the distribution of y equals to 25. Okay, 1 minute left. Let me finish slides. How about y is 10? How about its probability? Answer is what? Yep, thank you. Ah, okay. Sam, thank you. I see the chat. 0, exactly. Why is 0? Because when your x is from 0, 1, 2, 3, they are integers. When you're taking square, nobody going to be 10. Right? X squared, 0, 1, 4, 9, and then 16. Nobody going to be 10. So exactly 0. Okay? So then the last one is for x and bigger than 0, we have the probability y0, this guy square y. What if the square y is not integer right here? Easy, because Poisson counts It's everything's integer. So this guy also 0 as well as a probability. Okay, it's 45 right now. I'm going to finish my lecture. I don't want to drag you too long in my class. Okay, again, I cannot see you. Hopefully you can understand what I'm saying. If you have any questions, it's first class, email me, and then we can communicate to find a good answer. All I can see is that. All I say is that. Okay, if need any questions, let me ask the final one. If not, I hope you guys have a good one, and then I will see you on Thursday. Then if you're enrolled in 673, don't go away. I mean, yeah, go away, but I will see you in another room class. Okay? Bye-bye now. I'm going to keep it on, so in case you need to ask me something. Okay, I'm going to leave. How about that? So, okay.